Good morning. My name is Patrick Vinograd, and I am a managing software engineer at AdHoc. AdHoc is not a monitoring company. We build transformative digital services for the federal government. And one of the ways we do that, aside from a strong focus on user-centered design, is that we bring solid monitoring and ops expertise to the government space. The company was funded out of the successful rescue of healthcare.gov back when it first launched in 2013. But I'm here today to talk about some of our work at VA, the U.S. Department of Veterans Affairs. VA, in technical terms, in terms of its online web presence, operates, I would say, a pretty modest scale. It's not a Google or a Netflix or an MLB. But in terms of the actual services that it delivers to human beings, it's a big place. Every year it delivers north of $98 billion of direct benefits to veterans and dependents. It's also the largest single integrated healthcare system in the country, and it serves over 9 million veterans, provides them with healthcare. So as you can imagine, there's a lot of ways that somebody potentially would want to interact with the VA online. But historically, VA's online presence has been pretty fractured. So in 2016, we at AdHoc began working with VA and with the US Digital Service on a site called vets.gov. This was intended as a single site where veterans could apply for, manage, and track their benefits and healthcare. And it would be built in a user-centric way, accessible from the ground up, built on a modern tech stack, and incorporating best practices from industry. This is in contrast to a lot of government agency websites that you may have seen, including at the time va.gov. These sites may have information for the general public, but they also frequently have information about budgets, org charts, agency directorates, so a lot of sort of internal-facing information. Now granted, I cherry-picked this particular screenshot from the Wayback Machine, but you can imagine a veteran who's in need of critical services doesn't really care about VA's fiscal year 2019 budget submission. And while this may just feel like an inconvenience, remember that veterans are, in many instances, a vulnerable population. They're more likely than average to be experiencing homelessness or PTSD. And that means that a hard-to-navigate site can mean the difference between them successfully accessing services and giving up and not getting those services. So the vets.gov project was successful in its first couple of years, but it was really an experiment. It was on this secondary domain, vets.gov, not va.gov. But in around mid-2018, VA decided that they wanted to merge these two sites. So they would make va.gov, which is really the online front door to the agency. It's what comes up when you Google VA, a veteran-first site. It would adopt the vets.gov user experience and look and feel. And in particular, VA wanted this done by a particular date. They wanted to launch it on Veterans Day. For better or for worse, this couldn't just be a simple DNS cutover. All that original va.gov content that had accumulated over many years, while it wasn't presented in a particularly user-centric way, it was still valuable information. There was a lot of information about key programs that veterans needed, and even that agency-facing information about budgets and so on still needed an online presence. And then it also, given the timeline involved and the number of content owners, it really wasn't feasible to migrate all of that original va.gov content to the vets.gov hosting infrastructure in time for Veterans Day. So the team took a hybrid approach. Some of the key content would get migrated over. Other content would remain in that legacy hosting system. So we already had, this is a very simplified architecture diagram, but we already had a pretty typical setup involving an Nginx reverse proxy sitting in front of the different servers that we had in our infrastructure, and the Nginx would route traffic as needed to our content servers or our application servers. And then we just added the traffic for the va.gov domain into the mix. And we wanted to make launch day as small an event as possible. So we started by routing all the traffic for both domains through that Nginx reverse proxy, we would silently pass all the va.gov traffic to that legacy hosting system well in advance of launch. And then on launch day, we could be a little more selective and we could start routing the homepage and all the other content that did get migrated over to the vets.gov content servers and application servers. So this all got deployed. We were silently proxying the va.gov traffic through to their servers. And that was all working smoothly up until about 3 days before launch. So this is not what you like to see on a latency graph, right? We started seeing this big jump in latency for the traffic that we were proxying through to the legacy va.gov infrastructure. We trusted our metrics, but we followed this up with casual testing, and it showed that the site was becoming unresponsive, and this definitely obviously qualified as an incident. Days before a major relaunch, this could also cause our government stakeholders to lose confidence in this whole project and potentially pull the plug on this launch, and that was not something that anybody wanted. So we went through our incident response process. We established a dedicated incident response channel, and then we started sharing some basic information, started establishing some of that context and shared mental models about the situation, the environment, what we knew so far. One of the quick patterns that we noticed pretty early on was that the latency problem wasn't uniform. What we saw was two clear classes of reverse proxies. Some would start out healthy. Their latency would be within normal operating bounds, and they would stay that way. So that's some sort of the steady line of time series down at the bottom. And others would start out slower than expected, still within tolerable latency, but then at some point in their lifespan, they would spike to like a multi-minute average latency, and it seemed like they would never recover from that point. All right, so that's good. We have some sort of pattern that we're starting to identify. Two sets of instances acting differently. What's the difference? We started looking for any factor that would kind of neatly bin these two sets of reverse proxy instances and that we could use to differentiate them. And this is really where people kind of go to their homes and their background. So my colleague Craig is a networking person, so he goes there and he starts looking for a networking cause. But we looked at a lot of other different potential theories and ultimately discarded all of them. So we made sure that, even though we were confident in our deployment automation, we made sure that all the instances were in fact like running the same, based on the same AMI, running the same version of the code and configuration. That wasn't it. We made sure they were not segregated by availability zone. We made sure they weren't somehow serving different classes of content, one set serving bigger content, other set serving smaller content. We made sure there wasn't an issue with gzip compression or caching, or we started looking at the headers of the requests and responses and trying to differentiate. None of these really came up with anything, but we really wanted it to be an availability zone thing, right? Like, I think 5 different people in the incident response channel kind of brought that up, and that's because we had a clear mental model for why instances in different availability zones would potentially be experiencing different latency. Some network problem between AWS and VA that affects one zone or one rack. That would be a nice, neat story, but it wasn't that. Which leads us to the title of the talk. Literally pulled from the incident response channel. I was thinking about what else distinguishes these instances from one another. I knew that it wasn't a piece of data or a dimension of data that was going to show up in Grafana in our monitoring system. So I started kind of casually clicking around in the AWS console. I didn't find any counter examples there, but that wasn't really sufficient. So I wrote up a quick script that pulled data from Prometheus, combined it with some information from the EC2 API, and I came up with this. I'll just draw a dividing line. Does anybody see the difference? Yeah, so odd IPs, even IP instances with even IP addresses were fine. instances with odd IP addresses started out with higher latency, and they'd eventually spike to having terrible latency. Yeah, computers, right? I don't know if this is statistically significant with this set of instances, but the good news is we felt confident enough in our automation to redeploy the production reverse proxies and see if the pattern held up with a new set, and it did every single time. So yeah, we went through some stages of emotional processing with this. Now we had a pattern, but we needed to figure out why the parity of the IP addresses was causing this latency explosion. So we looked around a little more. And at this point, we kind of felt like we had to, work our way upstream and engage with our partners across VA and learn more about this legacy web hosting environment. But this early kind of piece of information that we shared early on in the incident response had sort of the kernel of the problem in it, which was that one option for F5 load balancing is that it can distribute traffic based on source IP, so partitioning based on the even or odd of the source IP. But that configuration was in place for a long time, so why did this only recently start happening? And the answer is that it was a hardware problem. So this is an SFP fiber optic module that was basically between the F5 load balancer and the web servers. The VA networking team had done a hardware upgrade or a hardware maintenance event, and they had inadvertently introduced a bad one of these into that web hosting environment. So all the traffic from even IPs was going to one web server, odd IPs to another web server. The ones going to the set of even traffic was going through one of these bad connections. Most packets were failing their CRC checksums. TCP did what it was supposed to do and started retrying and would basically initiate like a retry storm. And the reason that it started out bad and then spiked would be basically as soon as some multi-megabyte PDF got requested and routed to that web server, that's what would cause the instances to spike. There's a secondary factor which is kind of interesting, which is that we also had, I imagine that F5 configuration is intended to be based on the sort of the user agent, the original client IP address. At some point in the chain of instances, there was an X forwarded for header that was getting dropped. And so instead of using the user agent client IP, it was using the reverse proxy IPs. And I don't know if that actually made the situation better or worse in terms of our ability to diagnose it. But it definitely is interesting because that factor caused us to really overfit our mental model. We saw this sort of artificial two sets of reverse proxy instances, and that caused us to spend quite a bit of time looking at our own infrastructure, looking at these instances to see what differentiated them, when in reality the problem was upstream. And that's despite the fact that we knew that we hadn't made any deployment changes or configuration changes that aligned with the onset of this latency. But that extra factor made us kind of look in the wrong place for a little while. The good news is that it did give us a lever to mitigate the problem. So while engaging with the VA networking team took a while, we had to show our work and disprove some of the same theories that they were coming up with that we had already discarded. But in the meantime, we could at least start terminating any of the odd IP address reverse proxy instances, wait for auto scaling to bring back one, hopefully with an even IP address, and that mitigated the impact on end users. But once we got VA to replace that hardware, we quickly saw latency return to normal operating parameters across the board and irrespective of the IP address. So had a happy resolution. Ultimately, our launch otherwise went very smoothly, and now va.gov is a user-centric, easy-to-use site. All right, so fun debugging story, maybe a frustrating debugging story, depending on your frame of mind. What can we learn from it? First off, you are your dependencies. Obviously we've already heard this theme that your users don't care whether it's your problem or your upstream's problem. And in a lot of ways, it was really just a pure coincidence that this happened right before the planned relaunch of va.gov. But stakeholders, especially government stakeholders, can be pretty risk averse. And if this had not been diagnosed quickly, they could have easily decided to delay or even abandon that launch, and that would have meant a lot of months of work by a lot of people, ultimately for nothing. So if your service depends on any other systems, you really need to monitor those systems as closely as you do your own. At VA, where we have a mix of cloud and legacy on-premise systems, this means we try to do a lot of kind of longitudinal monitoring that lets us differentiate whether a problem is with the network path to that dependency or the dependency itself. And again, users don't care about that difference, but we do because there are two different teams that manage those things, that manage the network and the service, and so we need to engage with the right team for support. And then bringing this back to kind of the observability theme in this conference, we know that it's a good practice to make your dashboards include that idea of what changed. For example, annotating your graphs with deployment events. In this case, we do that. We annotate our graphs with our own deploys. But this external event, this network equipment upgrade, there was a system at VA that announced that change, but it required a human to log into a website and read that announcement. And there's really no good way of populating that information into our dashboards. So that's a little bit of a frustrating thing. And I don't even know, hindsight is 2020. I don't know if we would have known to track that particular event. It was sort of a couple steps removed from us. But in general, making your changes knowable as widely as possible across your environment is a step in the right direction. This is a sort of a side note, but something I ran across when I was looking through the Slack history for this. But remember your incident response process and be careful with it. So there's 3 things wrong with this message. The first is that this person wasn't the designated incident commander, so they shouldn't be directing anybody to make a potentially destructive change. Second, addressing an instruction to somebody instead of a specific person is only going to cause confusion or duplicated effort or nobody actually doing the thing that you want to do. And then third, of course, is that the instances with the even IPs were the healthy ones, and so if somebody had actually followed through on this, it would have made the problem much worse. Another point that kind of came up in our post-mortem analysis that maybe is not a hard and fast rule, but I think applies in this case, is that splitting operations can dilute responsibility. So if you read this comment, there's really 5 different organizations that are responsible for successfully delivering a request and a response to this legacy web hosting environment, and that's even before any of this change that I talked about, even before the vets.gov infrastructure was in the mix. VA has chosen to organize their IT operations like this. Maybe this is an extreme example, but I think it happens at a lot of agencies and even private companies where people see an opportunity for a shared service to get abstracted out and run, ideally more efficiently by a team that's focused on that particular domain and has expertise in that. But in this model, who's accountable for the website serving requests to users correctly? In some sense, it's everybody, and then so therefore, in some sense, nobody feels wholly accountable for it. And then the last point that I'm sure I'm preaching to the choir here, but it's something that we try to reinforce with our customers a lot, is really this virtuous cycle between monitoring and automation. If you only have good monitoring, you might know what the problem is, but you don't have any ability to react. If you have good automation, you can obviously make changes, but you're flying blind in terms of what changes to make. But if you combine the two, you have the information you need to make the right changes, you have the ability to make those changes, you can really start closing that feedback loop, and that's a very powerful thing. Thank you. Question? Yeah, I mean, essentially I was sort of hedging my bets that this cause seemed a little dumb, and I was like, I see something, but I'm not sure, but I can't find any counterexample. Yep. Can you clarify what you mean by confirmation bias? Yeah, I mean, I think so the question is about whether there was kind of confirmation bias at work, and any concern about, going the wrong way and potentially making the problem worse. So yeah, we did have an engineer who pointed out that if we turned off all the misbehaving IPs and we were going to start routing all the traffic to one web server, was it going to be able to handle that load? So that was an issue, and we confirmed with this other hosting team that they would be able to handle that. But in general, I mean, I think the overall theme is a little bit of confirmation bias, that we were looking at these reverse proxies and they weren't really the problem. Yeah. I think we would have coordinated. The question was, knowing what we know now, would we have done anything differently? I think we would have done a better job at engaging with those other teams and just being aware that there was a team that was doing, a hardware upgrade a few days before this launch, and that would have put it on our radar a little more effectively than having to go troll through that maintenance event website. Yeah.
How long did it take for them to realize it was a hardware upgrade? Or they typical, I'm sorry, everybody's a network guy. They typical network guys.
Yeah, so the question was how long it took to get buy-in from the networking team that it was their problem. I don't know the exact time. VA and government also doesn't always, do 24/7 support or, work as urgently as you might in industry. Since we were able to mitigate the problem, that took some of the pressure off. But once we were able to kind of show them the data, they believed it. They were able to look at their kind of F5 logs and see like, oh, there's a few million CRC errors, and that was pretty convincing for them. Yeah, so why weren't they monitoring, and why didn't they know they were getting these errors? I think that really goes back to that diluted responsibility thing. I don't know if we've fully fixed it, but we're at least aware of it. In the back? Yeah. So the question or comment was about that networking team could have caught this themselves, and then getting into networking versus application. So, yep. I'm sorry. It's an inside joke for some of my teammates who are watching the live stream. All right. Thank you very much.